Okay, so today we will continue with completing the functionality of our XMap. As you might remember from the last time, we have here a few functions which have not been yet implemented, so we will do that. In the last exercises we have, as you might remember, implemented an own iterator, so that one can iterate either through the entire map or iterate through all the entries in the map for a given key, as our map is set up such that if we insert an element with a key which already exists, then just a second element for that key will be inserted instead of replacing it. And this behavior, while in some cases useful, in others might not be. So what we will do now is we will work on our insert function such that we can specify by this additional mode parameter how we want the insertion to work. So whether we want it to add additional elements if some already exist, if we want them to replace, or if we want to insert and fail if an element of this key would already exist in the map. So the simplest case, of course, insert multi, is just inserting like here, but now if mode is not multi, then we will do some checking. So first we will check whether the element of the current with the current key, with the specified key already exists, and if it does, then we will either remove it and then the next will be inserted just by allowing insert pointer, or in the other scenario, if we set no replace, then we will return a failure. So first we will set up a short test case. We can reuse this. Here we have, for example, 0, which we are overwriting a few times. So normally we use the insert multi. Right, let's make this the normal case. Since until now it always was the normal case, and then here we can say, for example, that we want this to be a normal and the other one will make a no replace, comma. It is a bit not user friendly to have to specify the whole template here, but technically this probably is needed, since if we try this, the map complains that it doesn't have the full template specified, that it doesn't know what this map would explicitly be, even though these values are always the same. So an improvement might be to move this enum here just outside of our template and just call it, for example, cxmap __ insert mode, and then we will use this instead here. Oops. And what we also can do is well, we can also call it a map insert mode, and we can use an enum class which binds the values to the namespace of the enum. So let's go with this, and then since it's now in the namespace, since it is now in the namespace, we need always to specify that it comes from there. So this should be helpful enough. And here now we can replace this long template definitions with our enum class. So we have our nice test case, which we can easily test by putting a breakpoint here. And now what we need to do is to look in the map whether one of these elements with the set key already exist. So we have somewhere a get value function, if I recall correctly, that should do this. Yeah, get ptr, and it returns the value directly. So this is not quite what we would ideally you would want to have the as entry as such. Insert ptr, get ptr. we can just modify this function. It will need a small update, or we make actually, that's probably even better. We make a second function which we then call from the first function. So here we have our getPTR, which will not change much, and we'll have here get. For now, I will just call it getPTR2, and we need, of course, our entry type. So this one will return an entry type. It returns null, of course, if there is nothing to return. It returns null again, and here it just returns entry. So it's almost identical to what it did before. And this function for now we'll just replace with then is equals entry from key. Although we don't need this to skip mechanics. Well, but for now it's fine. Let's just go with the existing design. Now we return, if this exists, then return reference entry and a value, and then it else return null. So if entry is null, then the check is false and return null. Oops, there should be a double point here. And if entry is not null, then we will return the value from here. So now we can use the getEntry2 function in our insert function here at the top to get the entry, well, the first entry. The first entry, technically it's the last entry, so it always adds to the top. So what we are getting here first is the last entry with the right key, and our replace mechanism will just replace this. So first of course we check whether we found something, because if we didn't find anything, then we just continue with insert pointer down here. Now we check whether mode is no replace, because if it is, then we just fail. We'll put the breakpoint here, and else we return true. But first we need to replace the value. So entry value. Let's quickly see the definition of value. So value is, as you see here, just a own an own value. We didn't use any tricks to make value, and the entry shares the same memory or anything, so we can very easily just assign value to value, and we are done. So now in this case we have replaced the existing value. We could also define the function differently, namely such that it will return true when it inserted and false when it did not, which actually might be even a better idea, because then we have additional information. So now we check if this is normal, then we insert and return false in any case. Since we know what we provide as argument to insert, we always know what the return value means. If we provide insert mode normal, then we know that returning true means the element was added, and returning false means the element was replaced. If we provide insert multi, then it always inserts, so then the return value is technically not relevant for us. And if we provide insert mode no replace, then we know returning false means the element was not added, and return true means the element was inserted and it didn't exist before in our map. So let's quickly run this test case. Oh, something failed. Let's see. Right. When changing the function, I forgot to return the reference, since here we already have a pointer. Okay, so the first test case was, let's see, normal. Okay, so now we should have found that. We did. did we? Is it the right one? We look for 0. This would be 0, so let's see what we have here. We have hash. No, it's not right. Next is null. We didn't. Although, next value. Yeah, there's only one entry of this. So that might be right. Key 0 is right. Hash, apparently that's the hash that we compute according to a hash function. Let's inspect the value itself. Value contains the text 0. Yeah, so it's the right result. So now of course we check whether it's normal, and if it's normal we overwrite it, and then we return false. And now when we repeat it, here we should now have the new value replacing the older, so this didn't change, but value now contains the letter A, which is correct. And now since we have a different case, we don't replace it, and then we just return false. And of course all the other operations will behave as they behaved always, namely they will not change the content of our map. Sorry, they will change the content of our map, but will not modify the values. It will just add new entries to the map. It will not change the content of existing entries. That's what I wanted to say. So our insert functionality is now fully complete. We have a nice insert. We have a nice iterator. So the next thing we can take a look on will be removing of elements, and then we might need to revisit our iterator, since if we remove an element, then the list technically the list is changed, the map is changed, and our iterator might not point where we want it to point, so we will need to test whether how it behaves, and then of course might need to implement some mitigations. The simplest approach would always be to just require the user to advance the iterator to the next element, and then allow to delete the previous element. In STD maps, the deleting of entries with an iterator is made such that let's do if else. So in STL maps, the way how you work with iterators, I guess you could just advance it and then delete the before one, but the recommended way is to use the erase function, which takes an iterator and returns an iterator to the next element. So if you would have a loop which has some logic that which has should remove, and then it does something. Set should remove in some cases. Then if you have should remove, then you delete the entry and advance to the next iterator this way, and in the else case you just make the I++, which you would usually have had here in your for loop. So this is the STL way of doing things. I think for us this will be overkill, so we'll just tell the user that if they want to remove an element and then keep iterating through the list and through the map, then that they should just advance the iterator first and then use invoke remove on the copy, on a copy of the iterator that has been created before. One thing that we notice here at this moment is of course that our remove only takes a key or key and value. It does not take an iterator directly for removal, which we might need to add as well. So first of course let's just start with removing something by key. So let's say we want to remove the entry, any of the 0 entries. So map punct, actually we will duplicate the dump, and then we will, I should add probably some other printf so that we see before move and after remove. And let's add some empty lines. Okay, now we will just remove let's say 0, And now for us it would be to decide how we want the remove to work, because there might be multiple entries. So actually for the remove we will also add a parameter for p all is equals true. So by default we want to remove all the entries where the key matches our key. We could also set remove all to false, which would mean that we just remove the first one and then we are done with removing. And in the other case of this remove, we will match the value as well, so that we always only remove entries where the key and value match, which is quite a useful use case. So I often use that in various scenarios. Right, we forgot here semicolons, so we will add them. So we have remove 0, and as we remember, by default it already sets all to true, so we will remove all of them. So here we can no longer use an existing function, although that would be convenient. We will instead just grab the content from here. We can of course improve our remove by actually counting how many it removed, so that would be nice as well. Int tone. This might be useful in some scenarios, and it doesn't cost us much to add this functionality. So we will just add it. Of course, we check if m is 0, then we just return 0, because that means that the list hasn't got any entries yet. Now we go for the right bucket, and let's see. So we don't care for the key, we don't care for remove all. For now, we just want to remove something from our bucket. If we remember, our bucket is just a pointer to a S entry. So first we check whether of course it's null or not. And since it is a linked list, we will now need to kind of unlink the first element which we want to to remove. So to quickly make a reminder how this linked lists worked is, so we have our S bucket, which points to a S entry. That S entry's next points to another S entry, and so on and so on and so on until it points to null. So if we start from here and we want to unlink the entry, what we need to do is we need to set the pointer with which we are working currently to the next value and then remove the value that it had before. To make this as easy as possible and to implement it such that we don't have any special cases, like for example whether it's a bucket or a S entry next value, what we do is here, since S entry next as well as the bucket item are of the same type, we're here, instead of using a pointer, use a so instead of using just a pointer, we'll use a pointer by reference, which technically is just like using a pointer on a pointer, just that it is slightly more user-friendly to use it this way. So now inside here, inside the loop, we will first create a copy, pold, which is a copy of our value. And now here, at this point, when we set pEntry is equals pEntry next, then we already did the unlinking. The entry next might be null. And now the only thing that is left is to delete the pold element. This way of iteration, of course, ensures that we well, this way of iterating will modify all the entries, so we cannot iterate past something that we would want to keep. So at the very end, we will also have a if is not all, then break, because we only wanted to remove one and we removed one. And of course, we can increment our counter, but as mentioned, still we need to delete. let's quickly check how we created these entries. I don't remember whether it was new or malloc. It was a new. So we just need to delete it. That is super convenient. We don't need to even take care of deleting any other things, since value and key are just held by as entry. If they have any constructors, destructors, etc., deleting as entry will invoke the destructors for us. So just delete old, and this is already done. So this we don't need. This was just for a quick reminder how a linked list is constructed. So let's run our test case. We should be missing, well, no wait, it's for all. So we should have removed all the entries. Oh, I see a problem. I see already a problem. We need to validate the key. We need to validate the key, which means that we cannot just like this iterate. So I was a bit too quick with implementing this. A bucket may contain entries for keys which for different keys. There is no guarantee that one bucket contains only entries with one specific key, even though that would be the ideal case. It rarely is. So of course this in this case would fail. So we have here two issues. First of all, we need to check the key of the p entry, and the second thing is we should not modify the p entry if we don't need to. So actually we will need to use a pointer to a pointer, since we want to maintain our freeness of special cases. The straightforward way would be just to have something that has one case for handling the first situation where we are directly in the bucket, and then a loop that handles if it's one of the sub elements. But I don't like this style of programming. It's just very unelegant. So what we do here is, now we will have a pointer on a pointer. So here first of all we know that the pointer on the pointer is always valid, so we need first of all to dereference it and check whether what it is pointing to is null or not. Here we dereference p entry to get our order. Now before we do that, we need to check the key. So asterisk p entry to put this key. Well, if it's not equals, so if key is not equals key, then we continue. But we need to update the pointer before. So what we do here is we just set p entry to be the reference on the next entry, and then everything works. While here in this case, so we have our old already properly. So now at this point we know this is the element which we want to remove. So we have here our old pointer because we need it. Then p entry asterisk will be p entry asterisk next and reference. Oops. Right. Reference, so that we update this correctly. Then so only here we are unlinking, while here we are just advancing the pointer to the next element without changing anything in the bucket we are currently in. Then we can delete, count, and break. And now it should work. So let's try it. I think I already set a breakpoint. Nope, it's complaining somewhere. Right. Wait. P entry reference next. Right. We need first to reference this, and then we can do the next thingy. Just like I did. Wait. P entry is reference. Here we don't need this. Here we just want the value. We want to override the value with the right value. Now it should be correct. Let's try again. Okay. So we have here our list. We have bucket. Which one was it? Bucket 2, which contains all the A's. We have F, E, D, C, X, and A, and now here we removed all, so bucket 3, no, sorry, bucket 2. Bucket 2 contains 8, right, 8 was not a 0, so it worked perfectly. We removed from bucket 2 all the zeros, and we left the 1, 8 inside. So this works nice. Now just a quick test with the remove all parameters set to false, so that we see that only removing one entry will also work as it should. So we had F, E, D, C, and A. X is something else. Now we have just removed F, and voila. We could in principle add also an index, so we just remove one at a given index, but this probably will not be needed. It's better to just use the below a function where we specify a particular value we want to be gone. So here we remove F, and let's say we want also to get rid of, or we just leave it there. They want to get rid of D. So we now need to implement the other function. We could of course here also have like an all parameter in case we had inserted multiple elements with a given value. I think why not? We will just add this as well here, and the function is, we can make the function also return the removed count. So it will be quite simple. We just have to copy this and then add an additional test, not just for key but also for value, and that's already it. Now of course this is a bit not super elegant to have a function which is almost identical and only different in one line, so we will look into how to improve on this. But first let's check whether we have successfully got rid of D. So okay, so something failed. We emptied this completely. What did we do wrong? So we have our remove. Let's see, I have a suspicion this is a issue with which can happen. Yeah, as you see, we are entering the wrong function. The problem is that this also evaluates to a boolean, which is not cool, and our type is string, so our type is more complex, and since it kind of, we are giving it a char, but it expects a boolean or a string. So what it then does is, unfortunately, it defaults to using the boolean instead of using the string. So we will remove, we will call this second function with value. This way we can avoid this confusion. And now it should actually work fine. This is a error which one should be quite careful with, because as you see here, it's easy to alright, even better, wait, what, it failed? Here, value, unequal value. Value doesn't have a comparison operator, but didn't we define value as a CX string? We did, and thus CX string doesn't have a it should have an equals operator. I thought we have added that a long time ago. Where are the operators? To do add comparison operators, that was a to do. We have not added this. That is mildly annoying. Did we made this a homework? No, we didn't. We just forgot to add it. Well, that sends us on a short detour, since we need those. Then let's add them. So here's our to do. Generally, when implementing comparison operators, the the most convenient thing is to have a compare function which has a bit more complexity, but it then in turn allows to reduce on code redundancy. So we will create a int compare function which compares the current CX string with another CX string called other, obviously, as usual. And the way it works is if they are the same, it returns 0. If one string is larger than the other, it returns 1. And if the other is larger than the 1, it returns -1. So this gives us the flexibility to later implement is equals, is not equals, is greater or equals, is less, and less or equals operators, all 6 of them, just by invoking the compare function and applying the right comparison to the return value. So for now, here I either return 0, and we can implement the operators first. Is equals equals, zack, return compare other equals 0. 1 2 3 4 5 6. So not equals, that's not equals 0. Greater equals greater equals less equals, right, and I made one copy to match. There are just 6 of them in the end. So let's align that. Now let's think about the content of our function. So first, what we need to check is that both are not null. So if m is equals null, let's do that, yeah. So if m is null, or you can also write exclamation mark m. So now if other exclamation mark m, then so both are null, so return null. Both are null, so it's fine. In the else case, the first is null, the second is not, so the second is greater, so we return a 1. And else, here we need to check that m is still whether it's not null. Actually, we don't need the else since we always return. So this is null, and return just -1. Because we know that if we arrive at in the line 72, then we know that m is not null already. This is, I mean, the compiler, whether we have else here or not, will probably generate the exact same code because it tries to optimize. But realistically, it will not make a difference. It looks nicer for us. Maybe do it this way. It really depends on your personal preference. If we compile in debug build with absolutely no optimizations, that might have a small impact on performance, but for now, let's just go with creating more elegant code. It looks nice. I mean, or we could try to go for the most compact and write it like this, so it really is up to one's preference. Good, but anyhow, so now we know that both have an m, so now we kind of repeat the exact same test as we just had, just that instead of testing whether it has an m, we check the length of the strings. Or maybe let's write it by hand. So first of all, if naturally we can make it yeah. So if m what was what? Size is size and length is length. Size in characters in bytes. So we go for size in characters. Sorry, for length in characters, because this is what is important for us. So we go for size for length in characters. So if length is not equals m, sorry, other m or other m. Other m, it should have sorry, other needs a dot length um. So if they are not equals, then if we are larger than, if we are greater, then we return -1. We don't need an else, and return 1. So first we check whether the strings are even existing, then we check their length. We could in principle combine those in as far that we would always get the length and just fill in 0 if the length is different. But yeah, let's do it explicitly. I'm just thinking whether we have the right return value. So here we say if the current string exists. No, sorry, if the current string does not exist, but the other string exists, then it's 1. So here, if the current string is shorter, so let's do it like this way for simplicity. So if the current string is smaller than other, then return 1, else return -1. So now this should be proper. And now the last, of course, thing to do is to compare the content of the strings. So here we'll make a loop. Size t is equals null underscore I is less than length I plus plus. Now we know that the sizes are the same because we tested already and returned if not, so we don't need to check the size or the length variable of the other string. And now we just compare if m data from e is not equals other punkt other punkt p, what's the name, p data, sorry, first m then p data, p data from I. So if they're not the same, then we can just copy this, just apply it not to the length but apply it to the values of the characters. Wait, this is not right. Was it this direction? So if you length, no, it was this direction, right? So if here loop is equals, so if less than that, we return 1, and other and in the else case we return -1. And if we ran through the entire loop without having found a mismatch, then we just return 0 because this means the strings are the same. Okay, so this is done. This is done. We will now run this test case and expect it to work, and then we'll take a look into testing. Oops, we have a bug. And then we'll take a look into testing whether the comparison is exactly correct or not. Let's see. That would be a dot. Right here, so we didn't crash. That's already good. So we have here our D still, and here our D is gone. So that worked fine. And now we can just quickly check whether our X string comparisons are doing what they should. So say X string char test test null. In principle, we can even compare the same variable to itself. I guess the compiler will not try to optimize this away. Let's make it differently. In the release build, the compiler would definitely remove that fully. Right, we don't want to define it at the same time. But I think in the debug build it will do such a obviously unnecessary operation still. Yeah, you see it does. So we enter here, it's 0, 8, 0, and it returns 0. Right, and we also could use the compare function directly here instead of the operator, but yeah, that makes it better. Int test R compare with 0, and now we want a not null, so empty, which is just initialized with an empty string. So now we want to know how null compares with empty, and our test B, and our plan is of course that they should be functionally equivalent, because whether it's an uninitialized string or an empty string, it should be seen as the same thing. So here we had 0 and here we had 1. Alright, it returns 1 because we check this first. So that might not be the best thing. It really depends on what we want our string to do, so how we want it to behave. But I would say that ideally an empty string and a uninitialized string should be equivalent. So we'll in fact go here and modify this function a bit. So m question point m is equals m or 0. So here we just always default to using 0 instead of the value stored in m if m doesn't exist, and we will do the same for this one, for the other. Even though this actually it doesn't even increase the amount of operations significantly, since we do similar comparisons at the top. So we get rid of this, and now we have a special case if both are null. You have not this scenario does not take into account what is if both are empty. Well, basically what it wants is to just go. So sorry, the scenario doesn't care for the situation where both are empty, because it only compares the sizes. So we need now to, after we have checked that they are unequal, we need to check whether length basically will be 0, and if it would be 0, then not do anything. We could of course, so the easiest thing is actually to cache the value size tun, and technically we could cache the other value as well to make it as efficient as we can. So right, so what we do is we compare whether they're not the same, we check which one is smaller, if not then the other one, and here we just use the cached value. So if m does not exist, the loop will check for null, and then it will not do anything, and it will not try to access the other m's. Right, so this is actually a good improvement, even if it makes the code a bit more complex. And then we will, of course, not empty, but a and b. Let's already add all the test cases. So we want to test null against null, null against empty. Empty against empty, and empty against null. A, B, C. Then we want to test both of them against, let's say, A. whether A or B doesn't matter. And then we want test A against B, and that's actually all we need. So let's see what we will get as results now. But wait, what? Oh, no, we should of course test A against A just for good measure. Test A against A. It was complaining about something. About a small typo. So voila. Okay, doesn't... Right. Too much copy and paste. Small mistake. Good, so this should be null, it is null. Empty, empty should also be null, which is null. Here, empty, they all should be nulls. Yeah. So now we compare with 1, and it should be 1, because what we are comparing to us is bigger than us, because there's something. With empty is the same. A compared with BB is bigger than A, that's true, and A with A is 0. So it works fine. Let's get rid of that, or let's just comment it out, maybe we want to need it later for something. So we have validated that our comparison operator works as it should, so our remove value now also works. Right, and what we wanted to do is here to remove the code redundancy between those two functions. So what we'll do is we will add a another function. Technically it should be an internal function, so let's just copy this to our internal region. So we have insert get to, here we will add our remove ptr, where remove pointer, we will just leave the name at remove, and here what we will do is we'll add a function pointer which will where we can do can be two inputs. So we have a what we want here is to have a function pointer which will replace our line 363 with an on matching function. It will need to take an first of all, it will need to take an element of type pentry so that it knows what it has to do with, and then it will either need to have to always take key and value, and one implementation will just ignore value, and the other will not, or it will just take an abstract parameter and then extract the important information from this. And I think we will go with that abstract parameter approach, because this demonstrates how such things would be generally implemented. How such things would be generally implemented in C. So here we will replace the content of the line with our remove, with our match. We give it a dereferenced pointer to the pentry, then we give it a copy of our parameter, and if match is true, then we remove. And remove all, and the rest behaves the very same way. So we now go to our existing remove functions, and here we just say return remove, and now we need to write a lambda function, so a function which is defined locally. So we need, of course, our function prototype, which we'll just copy from here. Wait, that's not correct. That's correct. Function pointer definitions are a bit peculiar in their own way. So okay, we have here our remove. First we start with the capture list, which is empty since we don't need anything. Then we have the parameters, then we have the function body, then we have param, and param in this case will be just a reference on the key, and we specify all the same way we would always. And now here inside the function, what we want to know is we want to have the key. We could in fact don't use param and use the captcha list here, but this would then require us to use a more complex implementation. So there would be two options: either use a special STL provided function pointer, or define the remove as its own template, which we could do as well. But I think we will just go with the more classical, let's say, approach. So we have just key, reference, yeah, so we have key asterisk, key is equal, or we could also go with key reference, key is equals k asterisk from param. So this should, so first of all, reference key is type k asterisk, so we know k asterisk is param. And then since we want to have this kind of as a reference, we add this asterisk, although functional it will not do anything, since it will just treat then k as a pointer. So it will just make our key variable, which is inside the pointer, used as reference, hidden within a reference semantic, let's say, having the value of q. So it will not really copy anything except one pointer. So this is very efficient. And now we can make our comparison. Return p-entry key must be equals key, and then we repeat this for the other function, just that we will have a bit more of a problem, since we need to pass to it two variables, key and value. So what we do is we make a struct as params alright, and here we could actually make this const as well. The struct will keep a key and a value. If you would want to use str, we could just use a std pair, which is quite a convenient element. Params. From this we will instantiate a variable params params. Since it instantiates with a reference, we need to provide the values directly. Cannot do it by one. As params, and then here we just pass a reference to params, and then here key must be equals, and no, sorry, I think our comparison was unequals, right? So, but we will here keep it with equals and then add a negation to match, because the name match suggests that it should have a match and not that it should be unequal. So I think there is just a small bug further down. Here we forgot to negate the thing. Okay, so we go back here. We put a breakpoint here and test that everything runs as expected. Okay, we have a issue somewhere here. Okay, it doesn't allow us this way of initialization, so we will need to do it the long way. Zack doppelpunkt k gets k and v no, sorry, not k, key gets key and value gets value, right? And then here we'll just initialize it like this. That should work now. Okay, we still have some issue. But what does it confirm? Oh, we forgot the semicolon. It might have worked with the short in initialization Right. We forgot that we... So first of all, it probably would have worked with the short initialization method without the explicit constructor as well. I haven't read there, I just started fixing, so that's something that's not always recommended. The problem was we did not have a semicolon. The problem here we have is that we actually need the k variable to get the hash, but we don't pass key here explicitly. So I think for simplicity I will just add here a key const k reference key, and then we'll just pass the things twice. Since we are passing by reference, so effectively by pointer, it will not be a problem performance-wise to pass two arguments, and it maintains maximal flexibility for our match function. Actually, when I think about it, we could have even made this function available from the outside, because it's quite a nice thing. Okay, it doesn't like something we did. What is the problem? Let's see again definitions of our function. So we have our function pointer, we have the parameter we have key, this is boolean pointer void param. That should be fine. It probably is complaining about the void. So here, let's see again the error list. Where exactly is it complaining? It's complaining here. I mean, we can cast this to void asterisk to be explicit. Key should be fine. Bool should be fine. This returns boolean, so it should also be fine. I will change the name of the function to remove implement to obtain a more useful error message. It will then, instead of complaining why it kind of cannot find the matching function, it will just say which argument is wrong. Okay, cannot convert argument 1 from what? CMap char remove value lambda 1 to bool spec that should not cause issues. Do we need to change our C++ language version? 13 should be new enough. In principle, a lambda defined this way, so just defined with a empty bracket should behave like a normal simple function. So I'm not sure why is this complaining right now. We can debug that issue further by trying whether we can explicitly assign this. It will still throw an error. We just want to see where and what it says. Right, so first of all, we don't need to write this here and there. S entry. Somehow doesn't like our S entry. Not sure why. We have defined the S entry above already, so that should exist. Oh. small type, of course, small mistake with applying function pointers. That's obvious. Okay, now we have, let's see, this, it really doesn't like this thing. Even though it should be right, because here we only access params, here we only access entry. I mean, we can just force it to accept it. At least we should be able to. Right. Okay, that complicates things. Let's do it like this. Type def tab match. So we create a special type, which is our function pointer type, so that we can use it explicitly, like in a normal variable name, and then we just cast this thing on ATMatch. And now where is it complaining? Just doesn't want to cast our lambda function. Let's quickly see if that will behave better with a newer version. I mean, 13 is quite old, and they added some of the lambda functionality in later language revisions, but I don't think this will help us. Yeah, this was just a okay, let's do differently. So first of all, this should now, of course, throw an error in 9182. It should at least not longer complain. No, it still complains about something. Per entry goes from here. Oh, that might have been just a small detour, right? It would have worked out, right? I think we just it just contained a bug, and because it contained a bug, it could not properly compile. Here the compiler error was very non-helpful. It sent us on a wild goose chase, so to say. Right, so we create a string of the right type. Now we have here our parameter. We don't care for this. Now we enter our function here. Now we want to execute the match, so we will enter our lambda function. Here we have our params with our key and our value, and then we do the match. And let's see what we wanted. We wanted to remove the D and the D, and removed everything, so it didn't work. Oh, I know why. It should be end. Now it should be fine. Zack. Et voila. This worked as it should. So let's now test the last F9 function. This one is the simpler case. It's still complaining. Right, wait. Yes, impl. We forgot to change the name here, and as I mentioned already many times during these exercises, templates, template functions always cause troubles once they are invoked, and not just if they are there. What is complaining about? There is a typo in impeller. Params. Yeah, it doesn't like this. need to explicitly cast it to avoid asterisk, then it will be fine. And now false, so it should remove 1, it should remove f, and it removed f. And now let's last case just for completeness with remove all. It should remove everything that's a0. That's a 0 key, and it did. So this works already quite nice. Our map is I think mostly complete. Is there anything we would want? Right, we should test the delete case, but as I mentioned earlier, we will not go and make things too complicated by means of we will not make things more complicated by adding a array something function that allows us to increment our iterators and so on. We'll just here in this function say that we increment manually, well, that we need to increment first, and that's it. So we don't need to print it. We will want key and value. Although iterator would have an advantage, because then we could remove elements for a given key. We could remove elements at a given position, even if they have the same key and value. Here, the way we would operate is we would, well, test key and value, and if we want to get rid of them, we would then remove them using the remove value function. But since we don't have much time today, only 14 more minutes, so let's go with maybe the simpler approach first, and then we can see if we have enough time to make it more complicated. So we make oh, does our iterate actually has a copy it does not, but it should be copyable by default. So let's see, iterator for old is equals I. Iterator holds key and bucket item that calls only elements. So that should be fine. Then we increment it, and now we check if e value, we should use o, sorry, o value is equals 0. No, let's go by key. No, or we could remove everything that has an x. Yeah, let's go with this. If this is an x, so if the value is an x, then we'll use map remove value o key and o value. Okay, and now we run it, and the expectation will be, of course, that everything that contained an x will have been removed, and that we hopefully don't crash. If our iterator works correctly, we should not. Yeah, let's just see. And we crashed, so something is not quite right yet. The iterator destructor crashed. Why? Because we have key. Because we have a key which is not copied. We added the key without thinking much. We need to add a copy constructor because the key here will be created as a new element. So that adds some complexity, but not much. Well, so first of all, we add a empty constructor. we add a copy constructor, reference, oops, author, and this is just asterisk, this is equals other, this is equals other, and we need a assignment operator, so s iterator reference iterator is equals reference other, right here, so bucket index is equals other bucket index, bucket item does the same thing, bucket item m as well, and k is the one that was the problem. So if other key, and then key is equals key new key from asterisk other key. Okay, so now we ensure that we create a new copy of key if we need it, and well, we need an else case. Unfortunately, if key, then delete key, and key is equals null. Well, or technically we can put this in brackets, and actually we can simplify things. Now that actually we need this to be first. So first we need to delete any keys if there are any that we already have. So if we have a key, we delete the key that is null. If there is another key, then we make a copy. Now the operator is fine, so let's rerun it. Oh, but also this will not work because we always go for 0, and 0 does not have any access. Let's add here a 0 with an x so that we at least remove 1. So I'll put a breakpoint here that we see that we removed something. Still not working. This did not work obviously as planned. When deleting O, something went wrong. So let's put a breakpoint here and see what's failing. So we create a thing. Now we of course initialize all the variables, and now we use the I didn't use the assignment. Oh, sorry, typo. We didn't use the assignment operator because we did not create the assignment operator. Where? Right, and that should be by a dot. All be accessed by a dot. Right, now it should be fine. Okay, we didn't remove anything. The map contain a key. Wait, what do we want to move? We want to move everything that contains an X, and we added here a 0 with an X, so that should work. We have a 0 with an X, and we have a 0 with an X, so... No, we don't have it. Why? Oh, because we replaced something. Normal replaced our 0 with an X. Let's go with this. Now it should do something. Yeah, so one remove and that's it. So compare our list. So we have here our 0 with an x here. Now the 0 with an x is gone. And what we now also can do is we can activate one of the other invocations. Just quickly remove this. So let's go with that one. So now it should remove everything that contains an x, no matter which key it has. And voila, everything that had x's is now gone. We only kept the entries with text. So as you see, this works nice. And well, it might be in some way elegant to be able to remove at a given iterator. I don't think we need it, because if you have an entry with a value and a key, and we always remove starting from the top, then we will not run into issues with our iterator here. So I would say we will just leave it as is with regard to the functionality. And that would be it for today. We made a good progress creating a very useful own container type. If you have any questions, you can ask them. If you want, you can also ask them later by email. We'll see each other in the evening, or sorry, in the evening. If you take part in the lecture part 2, then we'll see each other at 3 o'clock. If not, then we'll see each other next week for the last time. So that's that. If that's already for you the end of the week, then have a nice weekend or have a nice Friday. Bye bye.